Hello, today we are going to discuss very important and interesting topic is torque effect of the plane rotator. The influence of a static electric field on the energy level of a diatomic polar molecule, especially, has been studied extensively by means of Rayleigh Schrodinger and perturbation theory. So, this approximation uh, problem may be considered model of rigid rotation. Okay? Therefore, here we are going to discuss the what is the effect of this static electric field on these polar molecules. So for that, we are considering the one rigid body with the momentum of inertia of a rigid body is I, and the electric momentum. So this is momentum of inertia, momentum of inertia, and the mu electric momentum. So here I am considering one constraint to the rotator in a plane about an axis is passing through its center of mass under the influence of the this uniform electric field E. So this is characterized by the Schrodinger wave equation. So generally Schrodinger wave equation we can write d squared psi divided by d pi square plus 2ie divided by h cross square. So this wave function psi, right? Uh, equal to equal to. So this is the potential energy. So this is actual uh, rigid rotator problem Schrodinger wave equation, right? So after substituting this static electric field uh, into the system, so potential energy of the system is created like this, and maybe is electric dipole momentum, and E is electric field and cos pi. Okay, so by using this Schrodinger equation, I'm going to write like this: d square psi divided by d pi square plus 2ie divided by h cross square into wave function psi. This is minus v psi equal to 0. So substitute this perturbation value here, I mean potential energy. Here minus is there. and plus uh, mu, it is better to use. I am going to write like this, E prime. Okay, cos phi wave function. Okay. So this is the Schrodinger wave equation of rigid rotator in the presence of static electric field of the uh, polar molecule. So which we considered here the that rigid rotator problem. This is the uh, rigid rotator problem. So we know here pi is the angle of rotation, I is momentum of inertia, already mu is electric momentum. It rotates in a plane about an axis passing through the center of mass. For example, uh, when this E prime equal to 0, the wave equation becomes like this: d square psi divided by d I square plus 2i e divided by h cross square into wave function psi equal to 0. So the normalized solution of this Schrodinger equation, the second order differential equation, is, we already know this one. This is general equation. So the normalization solutions are psi m of 0. So 0 you can use here. No, 0, okay, equal to 1 divided by root 2m e power I m pi. So this is the solution, right? Where m is value of m are 0, plus or minus 1, and plus or minus. So therefore the uh, energy values E0 equal to m square h square divided by 8 pi square I. So this is the unperturbed energy level. You observe here clearly. So this is Schrodinger equation. I'm going to write this Hamilton of this Schrodinger equation like this. The Hamilton and h is equal to minus h cross square divided by 2m d square divided by d pi square, okay, plus 1 divided by 2 m omega square x square. It is look like a that. Uh, okay, you can use here x square for understanding purpose. In addition here, we have to, one more term is there, mu e prime the cos pi. So if you look at this Hamilton, it is better to use pi Okay, pi square. So this is unperturbed term, and this is the perturbed term, right? This is the perturbed term. So this is just example. Okay. Here the potential energy is zero, which is why there is no potential energy here. Then we can get simply the solution. Okay. So this is very, very important. The energy level of the system is very, very important without perturbation. Now we have to calculate the perturbed term value. So the term minus mu e prime cos pi is perturbed Hamiltonian, right? So therefore the first order correction is n power 1 n h prime. Yeah. Here I'm not using any operating method. I'm going to use the integration products. Okay. Therefore, this is general formula, right? Here we are using m, right? So therefore, I'm going to use the m, not the n state, m state. E m power 1 equal to minus mu e prime is constant integral psi m power 0 complex cos pi psi m power 0 and d pi. So this is the first order correction energy. So in rigid rotator, right, it is better to use 0 to 2 pi. Okay. So we already know the solution of this equation, right? See here, psi m power 0 equal to 1 divided by, this is not m, pi. Okay, 1 divided by root pi, normalization constant, right? Root pi. So if I use the normalization solution, so this is the solution, right? Equal to 1 divided by root 2 pi e power I m pi. Okay. Here, if you apply complex, we can get minus here, right? So after substituting this wave function here, um, we can get like this e prime divided by root pi into root pi 2 pi. The remaining portion is 0 to 2 pi e power minus I m pi cos pi e power I m pi d pi. Okay. Minus mu e prime divided by 2 pi integral 0 to 2 pi. So e power I pi m minus m cos pi d pi. So e power 0 equal to 1, right? This portion is equal to 1, and minus mu e prime divided by 2 pi integral 0 to 2 pi cos pi d pi. If you apply integration, then you can get the cos minus sin theta, right? So minus into minus plus mu e pi divided by 2 pi. So cosine pi 0 to 2 pi. Sin 2 pi value is 0. Sin 0 equal to 0. Right? Therefore, entire equation, this term equal to 0. E m power 1. I got here the 0, which means there is no first order correction energy. So I need to go the higher order terms. Higher order terms. So for that, next I'm going to use the second order correction. See, the second order energy correction em power 2 equal to summation m not equal to n m the tetrapod Hamiltonian n, this general formula, second order correction energy divided by E n power 0 minus E m power. So we already discussed in last class this type of second order correction terms. If you get this type of equation, we have only two possibilities. Let us see here. So these are the two possibilities, right? One is the n plus 1 contribution term into n not equal to 0, remaining all the relation going to the 0. So I'm going to use this type of relation, right? So except these two relations, remaining all relations going to be 0. Therefore, I'm going to use similar relations here also. So you need to follow previous class. Okay, maybe it help you very lot. Em power 2 equal to. So if I use Hamiltonian term here, this is a Hamiltonian mu e cos phi, right? The square mu square e prime actually. So remaining two relations are, one is em plus 1 cos pi m, okay, modulus square divided by em power 0 minus E m plus 1 hours. Next important relation is cos pi m modulus square divided by em power 0 minus E m minus. Okay, similarly, if you use this normalization solution, right? So we already know the solution. Psi m power 0 equal to 1 divided by root 2 pi e power. So in case if you want n plus 1 state, yeah, m plus 1 state, psi m plus 1 equal to 1 divided by root 2 pi e power I m plus 1 into wave function psi. So this is the m plus 1 state. Similarly, you can use m minus 1 state also here. After using this m plus 1 state, m minus 1 state, okay, after using mu square e pi uh, here 1 divided by root pi, here 1 divided by root pi is there. So therefore 1 divided by 2 pi. The remaining portion is here the integral 0 to 2 pi. So this term is e power minus I m plus 1 pi and cos pi e power I m pi d. So this is square because of modulus square is divided by the energy difference we already discussed in previous class. This energy difference is minus h cross omega. Remember this one. So this energy difference is plus h cross plus h cross. So here I am using minus h cross omega plus similarly here also we can get if you substitute this wave function and this wave function also 1 divided by root pi 1 divided by root pi 1 divided by 2 pi common, then remaining portion here we can get e power I m minus 1 state, okay. Integral 0 to 2 pi e power minus I m minus 1 pi cos pi e power I m pi d pi whole square divided by h cross omega. So this is the equation, okay. This is the equation. So if you solve this uh, equation, then you can get uh, e m power 2 equal to 4 pi square I mu square e pi square divided by h square 4m square minus. After solving the steps here, you can get this one. This is the second order correction to the energy. So therefore, the total energy of the system is, we can write like this: total energy em equal to, this is em power 0, which means the unperturbed energy, ground state energy, and this is first order correction energy. This is second order correction energy. So for second order correction energy, only we can get what is the first order correction energy term we already discussed, right? This is m square h square divided by 8 pi square I. This is plus 0. First order correction energy I got 0. Then second order correction is equal to 4 pi square I mu square e prime square divided by h cross square 4m square minus 1. So if you want this solution, I'm going to recommend to go for Arulda's textbook or Arulda's problem solving textbook. So if you want this solution, how to get these values, so it will take a long time. This way I'm going to solve this solution. So directly I put here result. Okay. If you want solution, please try to comment below. I'll send you notes. So total energy after correcting m square h square divided by 8 pi square I plus 4 pi square I mu square e prime square divided by h cross square 4m square minus. So this is the approximate, I mean, the energy the system. So this is all about the uh, Stark effect of the plane rotator. So this is the some model problem. So what are the original problem we are going to face in research areas? As I discussed area is static. If you substitute an atom in a static electric field, because of electric field, the energy levels are influenced by the electric, right? So there is some perturbation terms are generated by using these approximations, especially Rayleigh, Schrodinger wave equation, and perturbation theory variation methods. So we can solve the different type of asymptotic solutions. Then we can find the what are the energy levels of the uh, system. So especially the polar molecules. Okay, it is a ideal problem to polar, mean polar molecules problem. Okay, thank you.